So the Casimir effect. The Casimir effect is something I learned about recently, and so I'm doing lots and lots of research into what we can use the Casimir effect for. And the Casimir effect, from what I understand, is when you take two plates, press them together, and the inside of that that vacuum that exists in between this creates this Casimir cavity, and inside that Casimir cavity or something, there's virtual particles and quantum fluctuations. So from there, you're talking about things that are so small or something or so tiny, but like if you could tap into this, like, say, fabric of everything that exists everywhere, these pockets of like whatever, and pull out from that anything and code it like with vibrational frequencies and whatnot to allow existence to come into existence from existence, then you can kind of 3D print anything from like nothing, or the everything that exists everywhere you look. So here, this is basically it, this explains it better, and I could be wrong about all this because this is quantum mechanics. I'm not an expert. Let's try again.
Okay, let's dive deeper into this soccer ball style plates concept, pushing the boundaries of imagination and theoretical physics. Soccer ball style plates. A deeper dive beyond geometry. Instead of just mimicking a soccer ball surface, let's consider plates with dynamically altering geometries. Imagine structures that can rapidly change shape, perhaps utilizing piezoelectric materials or other active components. Breathing cavities. Imagine plates that expand and contract, creating rapid fluctuations in the cavity volume. This could induce strong dynamic Casimir effects and potentially generate exotic particle states. Dancing cavities. Consider plates that perform intricate orchestrated movements, creating complex patterns of vibration and potentially manipulating the very fabric of spacetime within the cavity. Quantum field theory in action. Vacuum engineering. Treat the cavity as a controlled environment for manipulating the quantum vacuum. By rapidly changing the cavity's geometry, we might be able to excite specific modes of the vacuum, potentially generating particles or even influencing the properties of spacetime itself. Topological effects. Explore the possibility of inducing topological effects within the cavity. Could the changing geometry create topological defects in the electromagnetic field, leading to novel phenomena? Quantum entanglement. Entanglement generation. Investigate whether the dynamic interactions within the cavity could lead to the generation of entangled particles. Could the rapid changes in geometry entangle the vacuum fluctuations themselves? Technological considerations. Nanotechnology. Develop advanced nanofabrication techniques to create these intricate, dynamically changing structures. Actuation mechanisms. Explore novel actuation mechanisms to drive the rapid and precise movements of the cavity plates. This could involve piezoelectric materials, electromagnetism, or even optomechanical techniques. Quantum control. Integrate quantum control techniques to precisely manipulate the cavity dynamics and interact with the quantum vacuum. Flux capacitor. Inspiration. Energy density manipulation. The flux capacitor from Back to the Future implies a sudden, dramatic shift in energy density. Could we achieve a similar effect by rapidly changing the geometry of the Casimir cavity, inducing a sudden surge in energy density within the cavity? Spacetime curvature. Speculative. While highly speculative, could these extreme energy fluctuations within the cavity have subtle effects on the local spacetime curvature? Important notes. This remains highly speculative. Many of these ideas push the boundaries of current scientific understanding. Rigorous theoretical and experimental investigation. Extensive research is needed to explore these concepts further, including theoretical modeling, simulations, and experimental validation. Ethical considerations. As with any technology that could potentially manipulate fundamental forces of nature, it is crucial to carefully consider the potential ethical and societal implications. This exploration highlights the importance of interdisciplinary collaboration, rigorous scientific inquiry, and an open mind to explore the unknown. While the path forward may be challenging and uncertain, the potential rewards of understanding and manipulating the quantum vacuum are immense. I'm eager to hear your thoughts and explore these ideas
Anyways,
further. Do you have any
now I can
specific
show
ideas on
you
how
all
to
the
implement
advanced
these
math
dancing
behind all
cavities?
this because you may not believe that this is possible. So we go to a math program, an AI that's really good at doing the math. So go here. Oh, it's a coincidence. Show all the hyper advanced mathematical genius level quantum physics. So then, okay, here's a conceptual exploration of your soccer ball style plates with an emphasis on theoretical quantum physics. So this is talking about the dynamically altering geometries. I don't know what I have to learn what piezoelectric but here it all is. One could expect harnessing quantum foam. Ethical considerations. All right, well, let's finish up with this.
Okay, let's break down the equations and concepts presented in the previous response, providing a more in-depth explanation for each. 1. Piezoelectric materials. Equation. S equals D times E. This equation relates the strain, S, experienced by a piezoelectric material to the applied electric field, E, piezoelectric coefficient, D. This material-specific constant determines the magnitude of the strain produced for a given electric field. Application. By applying rapidly varying electric fields to piezoelectric materials, we can induce rapid and precise shape changes in the soccer ball-style plates. This dynamic control over the cavity geometry is crucial for our exploration. 2. Dynamic Casimir effect and particle creation. Quantized electromagnetic field. The electromagnetic field in a cavity can be quantized, meaning it can be described as a collection of harmonic oscillators, each with a discrete set of energy levels. These oscillators represent the different modes of the electromagnetic field within the cavity. Hamiltonian. The Hamiltonian for this system describes the energy of the field. The term T omega n, an plus 1/2, represents the energy of the nth mode, where Chi is the reduced Planck constant, omega n is the frequency of the nth mode, and an are the creation and annihilation operators for photons in the nth mode. These operators create and destroy photons in the respective modes. Moving boundaries. When the cavity boundaries, our soccer ball-style plates, move, the allowed frequencies of the electromagnetic field modes, omega n, change. This dynamic change in the boundary conditions can excite the vacuum fluctuations, leading to the creation of real particles, photons, from the vacuum. 3. Quantum field theory in curved spacetime. General relativity. In general relativity, gravity is described as the curvature of spacetime, moving cavities, and spacetime curvature. While the curvature induced by the moving plates might be extremely small, it's conceptually important to consider the interplay between the dynamics of the cavity and the underlying spacetime. Challenge. Incorporating the effects of spacetime curvature into the quantum field theory description of the Casimir effect is a highly complex and challenging task. 4. Topological effects. Topological defects. If the geometry of the cavity has non-trivial topological properties, like twists or knots, it can lead to the formation of topological defects in the electromagnetic field. These defects can have unique properties and may exhibit unusual behavior. Example. Imagine a cavity with a continuously twisting geometry. This could lead to the emergence of vortices or other topological defects in the electromagnetic field, potentially influencing the Casimir effect and particle creation. 5. Entanglement generation. Coupled cavities. If two or more soccer ball-style plates are coupled together, the dynamic interactions within each cavity could lead to entanglement between the quantum states of the electromagnetic fields in the different cavities. Cavity-mediated entanglement. The changing geometry of the cavities could mediate the interaction between particles, potentially leading to the creation of entangled particle pairs. 6. Technological challenges. Nanofabrication. Creating the intricate and dynamically changing geometries required for these experiments will demand significant advancements in nanofabrication techniques, such as electron beam lithography. For high-resolution patterning of materials, focused ion beam milling, for precise sculpting of three-dimensional structures, self-assembly techniques, utilizing self-assembly principles to create complex hierarchical structures, actuation mechanisms. Developing mechanisms to drive the rapid and precise movements of the cavity plates will require piezoelectric materials. As mentioned earlier, piezoelectric materials can be used to induce rapid shape changes. Electromagnetic actuation. Utilizing electromagnetic forces to control the motion of the plates. Optomechanical techniques. Utilizing the interaction between light and mechanical motion to control the cavity dynamics. 7. Measurement techniques. Highly sensitive detectors. Developing highly sensitive detectors to measure the subtle effects of the dynamic Casimir effect and the potential creation of particles will be crucial. This might involve superconducting detectors, such as transition edge sensors, TES, or superconducting nanowire single photon detectors, SNSPDs, atomic force microscopy, AFM, to measure the minute forces generated by the Casimir effect. Important considerations. Theoretical framework. Developing a robust theoretical framework to describe these complex phenomena will require significant effort from theoretical physicists. Computational resources. Advanced computational resources will be needed to simulate the dynamics of the system and predict the expected outcomes. Ethical and societal implications. As with any technology that could potentially manipulate fundamental forces of nature, it's crucial to carefully consider the ethical and societal implications of this research. This exploration provides a deeper dive into the theoretical and technological challenges associated with manipulating the Casimir effect using soccer ball-style plates. It's important to remember that this is a highly speculative area of research, and many of these concepts may not be feasible with current technology. However, by pushing the boundaries of our understanding and exploring novel approaches, we can continue to advance our knowledge of fundamental physics and unlock new possibilities for future technologies. I hope this more in-depth analysis provides a valuable Okay, let's delve into a more advanced theoretical framework, incorporating spacetime curvature and pushing the boundaries of our understanding.
Wait, let's see if we can get better results from here. The math actually is done. All right, well, I won't explain everything single equation. I might have to like ask it again. But
Okay, let's synthesize the vast amount of information we've explored, breaking down the core concepts and equations, and pushing the boundaries of our understanding. 1. Foundational concepts, Casimir effect. The Casimir effect arises from quantum fluctuations of the electromagnetic field within a confined space, e.g., between two parallel plates. These fluctuations create a net force between the plates, typically an attractive force. Quantum field theory, QFT provides a framework for describing the behavior of quantum fields, such as the electromagnetic field, in spacetime. It quantizes the field, treating it as an assembly of harmonic oscillators. General relativity. Einstein's theory of general relativity describes gravity as the curvature of spacetime. The presence of mass and energy curves spacetime, influencing the motion of objects within it. Spacetime curvature. In our scenario, the dynamic motion of the soccer ball-style plates can induce localized curvature in spacetime, even if on a very small scale. 2. Mathematical framework. Metric tensor. The metric tensor, G mu, describes the geometry of spacetime. In flat spacetime, it is the Minkowski metric, diag -1, 1, 1, 1. In curved spacetime, it deviates from this form. Lagrangian density. The Lagrangian density for a scalar field in curved spacetime describes the dynamics of the field within this curved background. It incorporates terms that couple the field to the curvature of spacetime. Klein-Gordon equation. The Klein-Gordon equation describes the behavior of scalar fields in curved spacetime. It is derived from the Lagrangian density and incorporates the effects of spacetime curvature. Mode expansion. Expanding the field in terms of modes allows us to analyze its behavior in terms of individual frequency components. These modes are affected by the changing geometry of the cavity. Bogoliubov transformations. These transformations relate the creation and annihilation operators of the field in the initial and final states of the cavity, accounting for the particle creation effects due to the changing geometry. 3. Soccer ball-style plates and dynamic Casimir effect. Dynamic geometry. The soccer ball-style plates provide a unique scenario where the cavity geometry changes rapidly and dynamically. Induced curvature. These rapid changes in geometry can induce localized spacetime curvature, even if on a very small scale. Coupling of field and geometry. The dynamic interplay between the electromagnetic field and the changing geometry of the cavity can lead to novel phenomena, such as enhanced Casimir forces. The complex geometry could amplify the Casimir forces. Particle creation. The changing boundary conditions could excite the vacuum and lead to the creation of particles. Topological effects. The intricate geometry could induce topological defects in the electromagnetic field. 4. Technological challenges. Nanofabrication. Creating and controlling the motion of the soccer ball-style plates with the required precision presents significant technological hurdles. Measurement techniques. Developing highly sensitive detectors to measure the subtle effects of the dynamic Casimir effect and the potential creation of particles is crucial. Control systems. Precisely controlling the motion of the plates will require advanced control systems, potentially utilizing feedback mechanisms and artificial intelligence. 5. Theoretical and experimental frontiers. Quantum field theory in strong gravitational fields. Exploring the behavior of quantum fields in more extreme gravitational environments, such as those near black holes or neutron stars. Quantum gravity. Investigating the interplay between quantum mechanics and gravity, which is crucial for a deeper understanding of these phenomena. Experimental verification. Designing and conducting experiments to test these predictions and gather empirical data. 6. Philosophical implications. The nature of reality. This research challenges our fundamental understanding of the nature of reality, the quantum vacuum, and the interplay between matter and energy. The limits of physics. Exploring the boundaries of current physical theories and searching for new phenomena can lead to paradigm shifts in our understanding of the universe.
Alright, can you go over each one of these math equations, though? Come on now.
Whoa! Some fireworks, huh? Who are you? I'm your guardian angel. Here's the bolt. The hell would I need a bolt? Take a look around. Oh, crap. Yep. Toss it into the anomaly, then while it resets, run like hell. Got it? Now go.
Certainly, let's break down the key equations presented in the previous response, providing a more in-depth analysis from a mathematical perspective. 1. Metric tensor, G min. Definition. The metric tensor is a fundamental object in general relativity that describes the geometry of spacetime. Components. It is a 4x4 matrix that relates infinitesimal distances in spacetime. ds squared equals g mu lr dx nu, where mu and nu range from 0 to 3 are representing time and 3 spatial dimensions. Minkowski metric. In flat spacetime, special relativity, the metric tensor takes the form of the Minkowski metric. E mean equals diag minus 1, 1, 1, 1. Curved spacetime. In curved spacetime, the metric tensor deviates from the Minkowski metric, reflecting the curvature of spacetime. 2. Lagrangian density for a scalar field in curved spacetime. Scalar field represents a fundamental field, such as the Higgs field. Lagrangian density describes the dynamics of the field. Key terms. Square root dash g, the square root of the determinant of the metric tensor. It accounts for the volume element in curved spacetime. Jane. The inverse of the metric tensor. Partial differential mu. The partial derivative with respect to the spacetime coordinate, x mu. Physical interpretation. The Lagrangian density contains information about the kinetic energy, derivative terms, and potential energy, mass term, of the field. 3. Action and the Klein-Gordon equation. Action. The action is a fundamental quantity in physics. It is a functional of the field and its derivatives. Principle of least action. The principle of least action states that the physical trajectory of a system is the one that minimizes the action. Klein-Gordon equation. By applying the principle of least action to the Lagrangian density, we derive the Klein-Gordon equation, which governs the dynamics of the scalar field in curved spacetime. This equation describes how the field evolves in a given spacetime geometry. 4. Mode expansion, separation of variables. The field can be expanded in terms of a complete set of spatial modes. Phi of x, t equals n area summation, nq n of t, psi n of x, where qn of t are time-dependent coefficients, and psi n of x are the spatial modes. Time-dependent boundary conditions. In our case, the boundary conditions for the field are time-dependent due to the moving soccer ball-style plates. This leads to time-dependent eigenfunctions, sin of x, t. Quantization. The coefficients qn of t can be quantized, leading to the creation and annihilation operators for particles in each mode. 5. Particle creation. Bogoliubov transformations. When the boundary conditions change, the relationship between the creation and annihilation operators in the initial and final states of the system is modified. These transformations, known as Bogoliubov transformations, can lead to the creation of particles from the vacuum. Number operator. The number operator, ARN, counts the number of particles in a given mode. The expectation value of the number operator in the final state provides the probability of particle creation. 6. Back reaction of quantum fields on spacetime, Einstein field equations. These equations relate the curvature of spacetime, described by the Einstein tensor G mean, to the energy momentum tensor, T mean, of matter and energy, energy momentum tensor of the quantum field. The quantum field itself carries energy and momentum. The expectation value of the stress energy tensor of the quantum field contributes to the curvature of spacetime. Back reaction. This feedback loop, where the quantum field influences the geometry of spacetime, is crucial for understanding the dynamics of the system. 7. Renormalization. Divergences. In quantum field theory, calculations often lead to divergent quantities. Renormalization techniques. Techniques like adiabatic regularization or point splitting are used to remove these infinities and obtain finite, physically meaningful results. 8. Challenges and future directions. Computational complexity. Solving the equations of motion for quantum fields in complex, dynamically changing geometries presents significant computational challenges. Experimental verification. Designing and conducting experiments to test these predictions will require advanced technologies and highly sensitive detectors. Theoretical advancement.